Teleportation will commence in 5 minutes. Do not leave any luggage unattended. Unattended luggage will be removed and destroyed. Attention, ladies and gentlemen. This is an announcement from Planet X31. Please take your seats. Teleportation will commence in 2 minutes.
X31. Please make sure that you have a cocktail in your hand. Science and Cocktails is an initiative taken by the Niels Bohr Institute together with Boonsloos, such that scientific awareness and scientific research can be brought closer to people. Science in Cocktails tries to give you a unique experience where you can interact with the scientist in person. Tonight's teleportation will take you billions of light years away from planet Earth. You will find yourself walking on mysterious planets where other life forms may exist. Uffe Gråe Jørgensen, Associate Professor at the Niels Bohr Institute and at the Center for Star and Planet Formation, will guide you on a tour through these unknown planets and digress over the needs and necessities for civilization to be born and develop. If any strange or weird life form will be encountered during this journey, the artist Henrik Schutz will represent it in his canvas. After a dazzling period of questions and answers, you will be guided towards the work of Rune Søchting and Jonas Olesen. Rune Søchting is an installation artist and music composer. He works on the intersection between sound-based art and music composition. Jonas Olesen is an electronic music composer and installation artist. He runs the record label BIN. Together they will present their work based on investigations of the sonic potential of electronic and mechanical processes such as electromagnetic fields, photoelectric sound, and micromechanical movements. End of transmission.
Okay, let's please give an applause to Uffe Gråe Jørgensen.
So welcome here, I'm happy to see all of you. I want to start with some historical quotes, right? So this is from Galilei. All truths are easy to understand once they are discovered. The point is to discover them. So he said so many wise things, and this is history. And this was the beginning of the Renaissance, and all these great people that made great discovery at that time is what we're reading about in history books and science books. We're also making history today, and that's why I start with this citation from this period. I want to tell you something that I think is history that has become just during the last few months. During hundreds of years, maybe thousands of years, people have discussed are there planets just like the Earth everywhere out in space, or is our Earth completely unique and it's only here that life can exist? Since a few months ago, we know the answer. And it's the first time in history that it has been known. And the answer is overwhelming. There is in our galaxy, the galaxy we live in, the Milky Way that one can see at night, there are 10 billion planets that resemble the Earth, that is more or less the size of the Earth, that is at such a distance from its star that it has a temperature just like here. In principle, life could exist there, but it doesn't. Right? Because if it did, if it was something that popped up every time we had a planet that resembled the Earth, there'd be lines of UFOs out there. There would be no space, right? They will come all the time. They don't, right? It was not space aliens that colonized the continents. It was human beings, right? So they don't come. Why not? I mean, if there are 10 billion places where they could come from, most of them are much older than the Earth. So this is, to me, a great mysterium. It's a great solution that we've had during the last few years and months, that we now know how many places there are in our Milky Way. But it just opens up for another mystery. Why are they not here? I mean, why are they not filled with space aliens everywhere? I don't know the answer, but As you know, everything is written in the Bible, so I want to start with a citation from the Bible. So it could be that this is the reason, right? Almost 14 billion years ago, God sat outside the universe, and then he called Gabriel and he said, well, you know, I think I will make a big bang. And after some time, water will appear, and life shall be based on water. But life where water is, but it should live where water is almost absent, and they should wonder about this. And in this way, the universe will be almost empty. And that way it became. I mean, I'm not so good in the religious things, so some of you may know where exactly it is in the Bible. I forgot that. But it is somewhere, and you can find it there. And what was it that God made wrong 14 billion years ago, so that it's not lining up with UFOs outside and there's life everywhere in space, right? It's very mysterious, and I'll talk a little bit about it tonight. I think one of the reasons is water. So water is a very unique thing. It's a very, very common thing in the universe. It's one of the most abundant molecules. But water in liquid form, like oceans and rivers and so, it may or may not be abundant, but we know it only one place. We've only seen it here on Earth. That's the only place where we directly have seen it. It probably is many other places also, but we know it's here. And it's completely fundamental for life. And that's why when we discuss if there's life elsewhere in the universe, we first of all talk about, are there places where there's liquid water? And we don't even know how water came to the Earth, and I will talk about that in a little while also. But all life on Earth is built on water. There's no life that is not built on water. It's the main ingredients. And 2/3 of the weight of our body is water. It's not such that we can make it drip out of the arm if we squeeze it. But 2/3 of it, what we have in here, we don't usually think about it, that actually life is a solution in water. So it's mainly water we walk around, and we are mainly water. And it's mainly, it has to do with the fact, you know it all, that if you take a bottle of oil, it's oil when it's in the bottle. But if you pour it into water, it becomes small droplets, right? So it's the interaction between the fat molecule in the oil and the water, which makes a small cell. And all life are built on small cells that are built with fat molecules. So in basically, chemically seen at least, we are basically just fat resolved in water, right? But it's all of us, so it's not a critic of anyone. So what is the problem with this, with water? Yeah, that is, life is made of water. And at the same time, it requires energy. Life is such a small energy machine. It's actually not any kind of energy, it's the kind of energy that we call entropy. And it's a very important concept, so I just want to say it. Most of you probably think that entropy is something you have not heard about, or if you have heard about it, you think it's something mysterious. It's just because we are not used to measure it every day. I mean, mass, for example, weight, is something very mysterious. None of us know what it is, right? But we are used to, in the morning, we step up on the balance and we look, what is my weight today? And therefore we think we know what it is, right? But we know nothing about it. And it's the same with entropy. So entropy is a kind of how energy makes order. And this is the basis of life. We are an ordered kind of thing that doesn't appear just by itself, right? So we're structured up. Energy flows into us and makes us order the molecules and the information inside us. And this is what entropy is. So energy is here in the inner part, close to the sun, and water is here in the outer part, quite far away from the sun. Life is a combination of water that is only out here and energy that is only in here. So this drawing here is actually meant to be a drawing of when the solar system forms. So you have a big cloud that collapses and it flattens out because it rotates. And in this disk around the thing that will become the star, or the sun in our case, the planets form by things that is condensing out of the cloud, things that becomes on solid form so that we can walk on it like the planet here. And it's a very simple thing, right? What I'm saying is it only snows during winter time, and you all know that, right? And one cannot make a snowball unless you have snow, right? It's no more complicated than that. So as long as there's just water vapor in the atmosphere, you cannot make a snowball. The same way here, as long as water is only as vapor in here where it's warm, it cannot form a planet, it cannot form a solid body like the Earth. So water can only form solid bodies out here. You can only make planets where water is out in the outer part of the cloud. You can only make life here in, and life is built on water. So it's mysterious how water came to the Earth. And maybe this is one of the reasons why there's not life everywhere. Maybe it's something that was very difficult to make. So in our own solar system, there's lots of water out in the outer part where the outer planets form, out where Jupiter and Saturn is. There's lots of waters. The moons around Jupiter and Saturn, they are mainly made of water. And the biggest ocean in our solar system, we think that it is below the ice of this moon that is called Europa, around the big planet Jupiter. So under here is probably the biggest ocean that exists in the solar system, and people are speculating, is that a place where life exists? And you can read science fiction books about this, but you can also read scientific literature about the life that may exist under the ice on the moon of Europa. It's heated because there are tidal forces, just like the moon makes tidal waves on the ocean here. There's very strong tidal forces between Jupiter and the other moons around Jupiter. This heats the planet from the inside, so they builds up small volcanoes. This is called black smokers. It's such kind of mini volcanoes that also exist at the bottom of the Atlantic Ocean and the Pacific Ocean on the Earth. So warm gas comes up from there. So the ocean, and this heats the ocean. So the ocean under the ice on this moon is warm. But there's lacking energy. There's lacking energy in the form of low entropy. That is the one that life thrives on. So there's no sunlight there. It's blocked from sunlight. There's not the right kind of energy. So I think, but it's only my belief, I mean, it's hopefully wrong, but I think that there's no life there because there's no sunlight, and sunlight is completely essential for building up structure. This is the way the plants build up and how we eat the plants, so we build up structure. And so it all comes from sunlight in the end. There's no sunlight down there. But of course, in the coming years, people will try to make space probes that will go up there and land on the ice and then drill through the ice and float around in this ocean and see if there's any kind of life down there, maybe around the black smokers down here or somewhere else. So we will have such probes as is drawn here that will come down and look at these places and will send signal backs and show us whether there are life forms in this ocean. Another place in our solar system which is quite surprising is a little bit further out where there's a very small moon. It's a picture of the moon here, a real photo of the moon, put in on a drawing where you see Spain here just to show you the size of it. So it's a very small moon. One could walk around it in a few days, and it would be a strange place to live. It's also inside a place where there's strong tidal forces that heats it up from the interior, and probably it's heated down here from the bottom, and then there's some places here in the ice where the ice melt, and one have water there, and there are chemicals from the interior, from the minerals down there in the rocky interior that comes up and mix with the water, and maybe this is basis for forming life. But of course, we have not seen any life there, and we have not seen any intelligent beings there. Nobody signaling to us from there, nobody flying down from there and greeting us. So if there's anything, it's microbes, but people will also try in the coming years to fly up there and see if there are microbes. And the way one realized this first time as a big surprise when there was a space probe that flew by this moon that is called Enceladus, is that it was seen that where Enceladus was here, there was such a ring of moist that was following the moon in its orbit around the planet Saturn. And this one could see only at a very spatial thing. And I think this is this is my favorite picture of the solar system. I think it's the most beautiful picture I've seen of any place in the solar system. It's a solar eclipse, but it's Saturn that makes the eclipse. So you line up the space probe just behind Saturn, so that Saturn eclipses the sun, just like the moon eclipses the sun from here, and we have total eclipse. But because Saturn has a ring around it, then of course this ring is outside and it's illuminated by the light from the sun. So it stands as a glory around Saturn, or whatever you would think. It lights up during this total eclipse. And when it's dark here, because of the total eclipse, one can see this very dim ring. You may be able to see it. And it's amplified here, so you can better see it. And what is completely fascinating, because of course you have to be in the plane of the planets in order to have an eclipse. So you have Saturn right here, and of course you have all the other planets inside toward the sun. And the Earth is very close to the sun, seen from this far away in the solar system. So the Earth is in the same plane. And actually, if you look carefully at the picture, you will see a small dot up here. That is the Earth that is seen during the solar eclipse by Saturn, from the backside of Saturn, between the rings of Saturn, because it's in the same plane, right? And if you really, really magnify this dot here to the maximum, which is done here, you can just see the moon on the side of the Earth. It's out there. So that's a solar eclipse by Saturn, where you can see the moon and the Earth in the ring system in the plane. I think it's such a beautiful picture. But that was just a sidetrack to tell you how one was figuring out that that Enceladus had this kind of environment where one could think that life could originate. There's water, there's hot water, and there's minerals that mix with the water that could form the first life. But otherwise, apart from these moons where there's lots of water, but there's lacking the energy, the solar light that I think is required for life to originate, but nobody knows, of course. Then the thing that resembles the Earth most is Mars, the closest planet to us, next after the Earth. And it resembles the Earth quite a bit. It has a solid surface that one can walk on. It has stones, and it has many resemblance to the Earth in many places, in many ways. And once back in time, billions of years ago, maybe 3 or 4 billion years ago, Mars looked very much like the Earth looked today. It had liquid water at the surface. It had a temperature more or less like here. It had an atmosphere, dense, maybe more or less like we have it on the Earth today. So that was a kind of place where life as we know it from here on Earth could have existed. And one of the big questions is, did it pop up on Mars? Is it such that every time we have the right physical condition, then life just comes? Or is there something else that needs to be there also in order that it comes? But 3 to 4 billion years ago, Mars may have looked like this. Today there's no ocean that has been drawn here, but on this picture of Mars, this part of Mars has been drawn blue to indicate that maybe there was an ocean there. This part of Mars is lower than the rest of Mars, and it has a very smooth surface, just like the bottom of the ocean that has been washed with water over a very long time. There's no craters or anything. So this could be understood as that there has once been an ocean, and you see there also inflow that could be rivers that flows into this ocean. So maybe 4 billion years ago, Mars looked like that. And maybe Mars, maybe life originated on Mars, if it comes just like when you have the right physical conditions. If this is so, then there's a funny twist to this, which is that Mars was solid at the surface before the Earth was. So it was prepared for liquid water to exist before the Earth was. So if life just originates when the right conditions are there, life will have originated on Mars before it originated on Earth. And if this is so, it has a very severe consequence for us, which is that whenever there is a meteorite that hits sort of at a low angle into the surface, it will push off pieces of the surface of Mars. They will flow into space and they will go in orbit around the sun. And most of this that are pushed out, it will fall on the Earth sooner or later, because it spirals in toward the sun, and sooner or later it will meet the Earth, and the Earth will act as a vacuum cleaner that will clean it up. Or even today, there's 1 ton of material from Mars that falls on the Earth every year around different places. Most of the times we don't find it because it falls in desert or in the ocean or on the Arctic or wherever that we don't come. But take a close look when you go outside. I mean, there may be pieces of Mars that falls down around there. There's lots of it coming. So this has been all through the geological history. And imagine that life just originated like this when the right conditions are. They were there on Mars before they were on Earth. Then the first life will have come to the Earth from Mars, traveling on such pieces of stones. And people have made experiments recently where they have shown that if you kick off such a piece, bacteria that we know from Earth could survive sitting on such a piece of stone that was kicked off by such an impact. It could survive 1 year in empty space, and it could survive the entrance to the Earth's atmosphere and the heat on the Earth's surface of such a stone. It would be still alive, and it would say, wow, now I'm on Earth. And it will walk out, and it will spread, and it will multiply around it. So that could have been the way life originated on Earth. And if this is it, then we are the Martians, right? And this solves an ethic problem, because people are discussing if we go back and if we want to colonize Mars one day, which I think will be in a few decades, then can we do it if there is life up there? Because we interfere with another system that is completely come by itself or so on. And it's all solved, you see, because we don't colonize Mars. We just go back. We came from there. So we've been away for a while, and now we're going back and see how it's going. So we can colonize Mars with no ethic problems. Right? So maybe we will do that. And there are nobody there. There may be microbes under the surface, but there's no bigger life forms. There's no advanced beings that are there. There's nothing that is crawling around on the surface of Mars or so. Before one was landing up there the first time, people were speculating that there were real animals or plants or such. And as recent as in the 1950s, you could see scientific papers in the literature that was describing how the forest developed with seasons on Mars. I mean, it was scientific papers in scientific journals that were based on observations with telescopes and so on, that astronomers wrote, and this was it. And if you go a little further back, then everybody believed that there were civilizations on Mars, and it was not a question of whether there was an intelligent civilization on Mars. It was a question of how do we communicate with it. And this small drawing that I have down here, that was a suggestion by the German mathematician Gauss, who suggested that the way we could communicate with them, that was that we should up in Siberia make 4 very big areas that were planted with different kind of grains with different colors, so that it could be seen from Mars. And they should be exactly this size here, structured in this way, because you may have recognized it already from your school geometry. This is Pythagoras' equation, or Pythagoras' sentence, which says that if you have such a square here where one angle is 90 degrees, the sum of the area of this one and this one is the same as, together is the same as this one, right? And so it should be planted this way, so that on Mars they could see that we knew Pythagoras' equation, right? So they would know we were kind of a mathematician and we were up to this level and we could talk with them about mathematics. So it was never done, and later on there were other interesting suggestions of how we should communicate with them. And around 1900 there was a great prize in France that was put out of 100,000 francs, which was a lot of money, to be given to the first person that established contact with a civilization outside the Earth, with the exception that it didn't count to establish contact with the Martians, because that was considered too easy. So you'll not get the 100,000 if it was only Martians you had contact with. It should be something more difficult. In 1979, this space probe here landed on Mars. It's not a picture from Mars, it's a picture from the test of it on the Earth. But it's the chief scientist, Carl Sagan, who stands here. And he had a strong wish. He was very influential on how the space probe was built. It was the first space probe that was ever built to look for biology outside the Earth. He had strong influence on how this was done, and he had different wishes, and there was one of the wishes that didn't come true, where there was too much resistance among the other scientists. This was that Carl Sagan wanted that on top of this space probe here, the Viking space probe, there should be spotlights that was turned on during nighttime on Mars, so that one could see during nighttime. But you can imagine that if one has solar panels and batteries that are charged by solar panels when you're 1.5 times further away from the sun than here, it's not much energy you have, and all the energy would go to these spotlights that should illuminate the surroundings. So the other scientists were not very happy. All the other experiments would have to be closed during nighttime at least. So it was in the end voted down. And Carl Sagan's argument had to do with this, that you think is just for fun, but it's really not for fun, it's very serious. Carl Sagan believed that he put out this scenario for the other scientists. He said, imagine we come up there to Mars. We have this fancy experiments in laboratory with us to study if there's life on Mars. And we measure everything and we take photos all around and there's nothing. We just see a desert. Then night falls and everything is closed down and nothing happens. And next morning, next Mars morning, we switch on the instruments again. And what do we see? Footprints all around the space probe, right? So we need to have light on in the night. That was so confident that people was, as late as 1979, that there may be such life forms as close by on Mars. Now we are more pessimistic with that. We don't think there's this kind of thing. So if we would have to find life forms, we would have to go further away. It's not in our solar system. There may be microbes somewhere, but any more advanced than that is not. Mysterious enough, somehow, but it isn't. So we'll have to go outside the solar system to other solar systems to figure out whether there's life forms there. And you know that people are listening with radio telescopes and have done it now for half a century and heard nothing. It's silent out there, and it's also strange, right? Because if there are 10 billion planets where life could exist, why are there nobody beaming anything? I mean, we don't hear anything. So the odds are not, as a beginning, so good. But so we will have to take it stepwise. And the step that have just been reached, which I started with, which I tell you that I think is a historical moment during the last few months, that is, we have come so far during the way that we have been able to establish how many planets are there in our galaxy where potentially the conditions could be like on Earth. And this is what we call the habitable zone. So habitable for places where one could live. So the places where one could live, the habitable zone, it means solid planets like the Earth, of more or less the Earth's size, that is at such a distance from the star that the temperature is such that if there was water, it would exist in liquid form. They would not be so cold that it would just be ice blocks. They would not be so warm that the water would evaporate and disappear. It would exist in liquid form, just like on our Earth, which is so essential for life as we know it from the Earth. So I've put in this diagram here the distance from the star in astronomical unit. That's the unit that measures how far is it from here to the sun. So 1 means the distance from the Earth to the sun. So a tenth of the distance to the sun, 1 distance to the sun, 10 times our distance to the sun. And then up here is listed the mass of the star. So one solar mass that is the same as the sun, 1 times the distance that the Earth has from the sun. Yeah, that means we end up here in the diagram. That is the Earth, right? So that's there in the diagram. And here are all the other planets in our diagram. And here listed in this yellow thing here, that is what is called the habitable zone. The smaller the star is, the closer you have to come into it, because it doesn't produce so much energy, so you have to be closer to it in order that you have the right temperature that water could exist in liquid form. So this is the habitable zone. So this is where we're looking for, can we find planets around other stars that lie along this band here. It turns out, unfortunately, that this is the most difficult region to look for technical reasons. It's much easier to find large planets at particular very small distances where there are nothing in our own solar system. But this is what we really want to know. And it's not only this whole thing, because when you get on the left side of this line here, then the planets are tidally locked. That means that they face the same side toward the star all the time. Just like the moon always have the same face down toward the Earth. It's tidally locked to the Earth, so it always shows the same face. So planets that lie in this part of the habitable zone, they always face the same side toward the star. So it will be terribly hot on one side and terribly cold on the other side. The atmosphere will probably freeze to ice on the back side and evaporate from the front side. It's not a place to live either. So even though it's in principle in the habitable zone, it's not really this part of it we want to find. It's this part here. So you see, we are limited to stars that are very close to one solar mass, very close to the same as our own sun, own star. Planets that lie more or less in the same region from Venus to Mars or something, about different stars. So this is the kind of planets we are looking for. And it's the most difficult, and that's why it has not been possible to do it for so long time. In this diagram, I'm sorry that there are so many things on it, and just close your eyes and take a nap meanwhile if it doesn't interest you. But I'll just explain you why it is so complicated and what it is that we're able to do in a few words here for those of you that want to know it. So this was the diagram I showed you before. It shows the habitable zone, where water in principle can exist. Here is the same thing, the distance from the star out along this axis, but on this axis here is no longer the mass of the star, but it's the mass of the planet in units of Earth mass. So one is where the Earth is at one distance to the sun, so here we have the Earth. That's why there's an E in this triangle there. And the other planets in our solar system, they are here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And you see they fall along such a line here in this diagram here. This is where we expect planets, at least planets as we know them from our own solar system. And the different technique we have 3 different techniques. One is the Doppler technique. This is this one. All the black triangles here, they are planets around other stars that have been found by this technique. It's a technique where when the planet orbits around the star, we always say the Earth orbits around the sun, and this is almost correct, but not quite. The completely correct way to say it would be that the Earth and the sun orbits around their common center of gravity. But it's almost the same as saying that the Earth moves around the sun, because the sun is so heavy compared to the Earth. So the common center of gravity, it's deep down in the sun, close to the center of the sun. But the Earth's movement makes the sun move a little bit around in a small circle that takes 1 year, because the Earth pulls it in different direction. The larger the planet is, of course, the more it pulls to the star. And one can measure with a spatial technique how such a star stands and moves toward us and away from us, because it moves in small circles. And it's just a technological development. It was known 70 years ago. It was first suggested one should look for planets around other stars in this way, but one didn't have the technique to do it. It was not possible. This has been developed over the decades that followed, and today one can measure if a star that is 100 light years away from here, 100 light years out in space, if it moves toward us and away from us with the speed that a turtle walks. We can measure it. Right? So fine-tuned are the instruments. But this is not fine enough to see Earth-like planets. You can see Jupiter-like planets, the giant planets in our solar system, in this way. So therefore, all the planets that has been discovered, they're big, just like Jupiter and Saturn. They're up here in this part of the diagram. That's what you can see with this technique. Then there's another technique that people are using. If you have a star and you have a planet that moves in front of it, and that we are exactly in the plane, so it comes in front of us, in front of the star seen from us, then it will dim the light a little bit. This is called a transit. So when it goes in front, the light from the star will dip a little bit while it's in front, and then it will go back to normal. Next time it comes, it will dip again. So if one sits and looks for the light with high accuracy on the stars and sees such periodic dip, one can understand there is a planet that goes in front of it. And one can infer how big the planet is and in which orbit it goes, because one knows how often does it come. Right? So this method is best if the planets go very quickly around the star, so we see it coming very often. Then we can most easily see there's a period. Therefore, transit planets, they are in here. But you see, the planet in our solar system were out here. So both of these are in regions that can discover planets that we don't know from our own solar system. And it was a big surprise 15 years ago when the first planets were discovered, that there at all was planets that we don't know of in our own solar system. So that's the main conclusion now from these things, that there are lots of planets that are different from the planets that we have in our own solar system. In order to understand whether there are planets down here where I've drawn a small house to indicate it's a habitable zone where one can live, then one needs other techniques. You see that this doesn't really come into this area. And I will not go into details with it, but we actually have taken an initiative at Copenhagen University together with Aarhus University to build a network of small telescopes that will be particularly sensitive for a method that is sensitive to this region over here, where all the planets in our own solar system exist. It's something that requires lots of observations, but not big fancy telescopes, rather small telescopes that will be put around the globe at different places. So it's also very exciting to be part of, because you have to go to China and see whether it should be put there, and to South Africa and other places. So it's a nice project, and I will not talk more about it, other than hopefully in a few years we'll find a lot of planets that resemble very much the Earth and Venus and Mars, if they exist around other planets, that are completely resembling our own. So these are the methods that one is using to look for planets around other stars. And maybe some of you will think how stupid he is. He didn't think about just taking a camera and taking a photo and see if there is a planet next to the star. And it's of course a very good idea. It's just not possible. And it is not because that the planets are too dim. If they stood alone on the sky with large telescopes, we could see them. But the fact is that they stand right next to a star that is typically 1 billion times brighter than the planet. You cannot see them because they fall into the light of the star. So not so long time ago, I used to say, it will never be possible before we will get space probes out that can do very fancy measurements out there. And a week after I said it last time, there came some measurements from the Earth that showed the first picture of planets around other stars. So I don't say it anymore. And I also tend to not saying it will never be possible to do something. I mean, sometimes one gets surprised. So there are a few planets, there are about 10 planets that one have actually photographed directly. But they're little spatial planets that are on big distance from their star and that are exceptionally bright. So in general, one cannot just photograph a star, but has to look at it indirect. What has happened during the last couple of years, and in particular the last month, are 3 things. These 3 techniques that I told you about, the Doppler movement and the transits, and then the thing that I'm involved in myself that is called microlensing with these new telescopes we are doing. These 3 methods together can be combined to say something about how many planets there are of different types. And in particular, many planets have been discovered with the transit method by a satellite that was launched in 2009 and is now beginning to roll in with results. And about 2,000 new planets have been announced during the last few months from this satellite by itself. And this is amazingly many, because before that there was only known 700 planets from all other methods. So here it's suddenly 3 times more. But it's not so much the number, it's because it's done with one instrument. One can make statistics on it. We know exactly how it was done, and they were all discovered by the same telescope, by the same method, so we can draw statistical conclusions out of it. And what this satellite does, that is drawn here, it looks up in a particular place on the sky near the constellation of Cygnus, the constellation of the Swan, that one can see here in summertime. And it looks at a certain field there in the Swan, and there are 150,000 stars that it can transmit data down from. So it keeps photographing for 4 years. It will just take photo of these 150,000 stars all the time. And then it will send information down. How bright was each of the 150 star when it took the last photo? And then periodically there will be something that goes in front of some of them, and this will be planets. And that's how one discovers the new planets. And it turns out that there are many, many, many of them. And it's also based on this, together with the 2 other methods, we can now for the first time say something about how does a standard solar system statistically look like. And a standard solar system, we can now say with quite confidence that it consists of two planets, 2.5 statistically. One that lies in where we have no planets in our own solar system, inside the orbit of Mercury, very close to the star. One that lies more or less in an orbit that resembles the Earth and is more or less the size of the Earth, and one that lies a bit further out. But the gas planets that we have in our solar system, they're very, very rare. It's nothing that is around, it is common around other stars, which of course makes one think immediately, so we live in a special place where there are gas giants. And the moment that one says it comes out that we live at a special place, there's some bell that rings and says something is wrong, right? Because we've done it so many times. We thought we lived in the center of the universe and everything circled around the Earth. And when this was turned out to be wrong, and it was, one could not resist anymore to believe that it was wrong, it was at least that the sun was the center of the universe and we were moving around of that, and then everything else was sitting on glass spheres around us. And then when this also didn't hold, we lived in the Milky Way galaxy, then at least this galaxy was the center of the universe and all the other things was around that. It was not like that, and now we know there is no center of the universe. And so it has sort of been raised to a philosophical principle that every theory shall fulfill that we ourselves live at a random place in the universe at a random time. Otherwise it's not a good theory. But here we have a theory that says we live at a spatial solar system that has these giant planets that is not normal. It immediately calls attention, saying, so were these giant planets out there necessary in order for us to be here? Is that why we are at a spatial place? Because then it's no longer spatial. I mean, if this is required in order for life to originate, then we are here because we could not be at any other place, because the places where they didn't have this spatial configuration, life could not originate. Right? So maybe Jupiter, the existence of Jupiter and Saturn is one of these things that was necessary for water to be here, for us to originate. And I will go a little bit deeper in that in a few seconds. Just first tell you that this is what the transit planets that one knew before the Kepler mission, before this satellite. And you see they are all the size of Jupiter. They're much larger than the Earth, and they're in very small orbit. It takes them typically a couple of days to go one time around the star, so they're very close to the star. These are the planets that one now know from this single satellite experiment today. And one of the very important things is that you see the many more small planets of Earth size, and those that are really Earth size one cannot see because it's too difficult even for the satellite. So one has to make some assumption of how difficult is it, so how many more are there than those we see because it's difficult, and try to make up for this and get a good number. And when one do that, the most reasonable number says that there are about 50 times more Earth-like planets than there are large gas giant planets in a typical solar system. and it's always 50 in all kind of orbits out through the system. This is a little bit combined with theory and some things. That means that one can use the measurement of the giant planets to see how are they distributed, and say we know that everywhere else there are 50 times more of the Earth-like planets, even if we don't see them. Right? So in this way we can know something about how do the Earth-like planets distribute to a standard solar system, and they are the most common one, so they are those that are there. And the result of this is, all of this is that about 1 out of every 20 stars has a gas giant somewhere in the system, usually in small orbits, not out there where they are in our solar system. And there are 50 times more Earth-like planets than there are of these big ones. So that means 1 out of every 20 has such one, 50 times more of these. That means there are on the average 1 over 20 times 50, so there's on the average 2.5 planets that are Earth-like, Earth-sized, on a standard star in our galaxy. There are 100 billion stars in our galaxy, so there are 250 billion Earth-like planets in the galaxy, but not all of them are in the habitable zone. So if we reduce it to say those that are in the habitable zone, it's 1 out of 25 of them that are in the habitable zone, and that means that if you multiply this, that are 2.5 with 1 over 25, you get 1/10. So 1 out of every 10 stars has an Earth-like planet in the habitable zone. So this is the main result that comes out of this statistics. And then comes this enormous surprise. I mean, because it's very many, it's 10 billion stars in our Milky Way galaxy. And if you go only out into 100 light years from here, I mean, 100 light years is nothing, right? Then there are 15,000 stars within 100 light years from us. 1 out of every 10 of them has an Earth-like planet in the habitable zone. That means just within 100 light years from here, there are 1,500 planets that resembles the Earth, where life could have originated if conditions were right for it otherwise. I mean, they are in the habitable zone. This is what I start calling the trading zone, right? If you know some politicians that shall put some effort into that, we should make more research in this. This is where we could sell goods to and such things. It's nearby in the surroundings here, on less than 100 light years away. And there are lots of them. So why are there why don't they come all the time? I mean, you can say, well, of course, 100 light years is a lot. It would take us with the speed of light, which we all know is the maximum speed one can go with according to what Einstein said and according to what we believe. It will take at least 100 years to go there. It will take even 100 years if we send a signal that say, hi, here we are, and then 100 years later it comes out there, and if they manage to receive it, they can receive it and say, wow, they are there, and they send a signal back and say, hi, here we are here, right? And then we get it after 200 years, and we can speculate about what shall we then say next, right, and so on. It's a little bit stupid conversation one can have, but maybe interesting to know that they are there at least. But that is with our present day knowledge that we can do this, right? Imagine that we go just 1,000 years ahead. Who will bet on what does technology look like in 1,000 years? Or even maybe we can envision what it will look like in 20 years from now. And we can have some fantasies about what it will look like in 100 years. But 1,000 years we're lost, right? It's the same as if the Vikings should sit in their boats and say, I'm sure that they have mobile phones when we're 1,000 years ahead, right? I mean, how could they? They could not have this idea, right? It's things that we have no idea of that will come in this time. And if we go 10,000 years or 100,000 years ahead, we have no clue to what it looks like. So I don't think we should say that it's beyond the trading zone. I mean, it's fair to call it the trading zone, but it will not be tomorrow we will trade with them. So with some technical development, we'll be able to do it. It's within the nearby. So I cannot imagine that they would not, if there were people, if there were technological civilizations there, that they would not come here all the time. and trade with us or eat us or whatever else they would want to do, right? I mean, it's a question that is always open. Should we try to reveal that we're here? Should we send a signal out there or should we not, right? Some people have already done, and it's a question of was it a good idea, right? Because in some years they'll get this signal and they will see here they are and they look like that and here's something we can eat, or I mean, and then they come, right? If they are like that. Or maybe if they're good people, I mean, then they will send us a message and say, now we tell you how you should do in order to have a good life, or something. I don't know, right? I mean, nobody knows. The famous scientific science fiction author that is called Arthur Clarke, he was of the opinion that this opposite to this, that some people think it's dangerous. He said, send all the signal and do everything we can to get in contact with these out there, because they are good people. Because aggressive species that lived out there, they will have destroyed themselves. Maybe right. I mean, maybe that there's some unfortunate thing in the evolution that those that becomes the dominant species on the planet, they're those that sort of elbow themselves forward and sort of manage to squeeze out the other species and the other kind of things that live there and become the dominant one, like us. I mean, not like any of us in here, but the other ones, right? So maybe this is built into evolution, that this is the way it goes. And such species, they have no chance. They die out. So maybe there is a blocking there. Maybe that's why there's nobody out there, because it always goes like that. So maybe it's, no, there was somebody that says no. I love that. Just say no, right? Because I also think no. We just have to make more effort in United Nations and all these things that we're doing. I mean, it's the only way to go. I mean, imagine, it's amazing just this fact that all nations sit in one room and talk to one another. Imagine chimpanzees doing this, right? It would be impossible, right? So we have reached somewhere, even though we think it's too little, it comes. And maybe we will manage over this step and we will be the good ones that will tell the other ones. This is what this guy here thinks. He's called Enrico Fermi. He was a physicist, an Italian physicist that settled down in Chicago, and he made this that is now called the Fermi Paradox. He said there are no technological civilizations out there, and I tend to think the same now, and I think that his paradox becomes even more a paradox than he could ever have thought, now that we know that there are 10 billion places where they could live, but don't, right? As he also envisioned. In the other end is Frank Drake, who's very optimistic and thinks that we should just listen long enough and we'll get these fantastic radio signals where they tell us all things about life and we'll communicate with them. And Frank Drake wrote this famous equation which tells that the number of civilizations, technological civilizations in the Milky Way galaxy, which we can communicate with, it's equal to, and then there are some factors over here on the other side. It's a little bit strange mathematical equation because it's different from most mathematical equations, because on the left side we have something we don't know which we would like to know. On the right hand side we also have things that we don't know. So one can say at the first thing one could think it's not so useful, but it is very useful, right? Because what it does is that it divides this thing that we doesn't know, how many can we talk to, up into what is it we need to know in order to figure out this. How many stars are born per year or per time unit, times the fraction of those stars that will have planets around them. We know that now, right? They didn't know it in 1961 when he first time wrote this equation. We know how large a fraction of these that have planets have Earth-like planets. We don't know how large a fraction of the Earth-like planets develop life. We don't know what is the probability, how large a fraction of places where life developed, will it develop into intelligence? We don't even know what intelligence is. So that's another problem. But how often will it happen? And how often will intelligent life tend to construct a radio so that they can send signals, right? This is also another factor that goes into it. These are the factors. And then, of course, comes in the end something with time, because it's how many are now, and this starts with per time unit. This is how long time does such a technological civilization live. We also don't know it. Right? We have just begun. So this is, and he thinks that there will be lots of them. But Fermi thinks that there are none. And his arguments are very interesting, because he says that the way that human beings are is that we tend to spread all over where we can be. So we moved out of Africa some tens of thousands of years ago, or we didn't, our forefathers did, and they spread all over the globe, and now we're everywhere, right? And soon we will make a colony on the moon, and when that is done, it will be in 10 years or something. There will be the first commercial flights up there in a few years. They are already ready. Then from there will be the colonization of Mars. I think it will be in 20 years or something. We will all see it. But we can talk about it in 20 years. But I think it will be. And humanity will spread all over the solar system, and when that is done, it will spread all over to the next stars where we can go to. And again, we need a little more technology than we have today in order to go to other planetary systems. But there's nothing against that it can be done. And in Fermi's opinion, he put some numbers and said, how long time will it be when people have settled at some place and they're bored with there, and some want some new challenge and they go to a new place. Just like if you think about ourselves, the Europeans that were here, and then we were bored or there were other problems. I don't know what the problems were, but people thought it was worth to go over the Atlantic and be in America, even though it was very complicated, and many of them died, and it was a very expensive and difficult travel over the Atlantic, and most of them knew they would never come home again and see their family anymore, right, when they went there. Now we are toward the same challenge. Some people will go to Mars. It's not easy to come home and just visit the family, but it's the same kind of challenge as when the first people went to America. It's another kind of challenges that will meet the people that go to Mars, right? The people that went to America, they had some challenges with how do they find work, and how do they handle the engines, and all sorts kind of things, right? There would be no engines on Mars. There would be no any of these kind of things, but there will be no atmosphere, and that will be another kind of challenge, right? So they have to put up that, and some people will find it fascinating to be the pioneers that will do this kind of thing, and here we'll go forward. This is, according to Fermi, and I think he's right, something that is built into our nature. So if this is correct, then we will spread over the Atlantic to the moon and to Mars, and those that are colonized on Mars, they will think that now we will try to meet new Italians, and they will colonize something else more difficult, maybe the oceans under the ice on Europa that I started to talk with, and a certain state they will move out of the solar system in one way or another that we don't know about today, just like the Vikings had no ideas that there would be jumbo jets and such things today. If they were asked how would people do in 1,000 years, they will maybe draw faster ships or something with more sails or something like. But here some breakthrough will come in technology, and they will go there. And in Fermi's calculation of what would be reasonable estimates for how often would people think now we want to go new places, he ended up with a calculation. You have to think this is something that grows exponentially, right? You come out at a new place, they split out to 2 new places, each of them split out to 2 new places, and very quickly it spreads all over a very large area. And this calculation that Fermi did with such reasonable, what he thought was reasonable estimates of how long time does it take before they want to go somewhere else. He calculated that in 5 million years, humanity would have spread all over the galaxy, all over the Milky Way. And this is quite astonishing. Whether one likes it or not, I don't know really. I have not made up my mind on that. But it's somehow scaring to think that maybe in 5 million years, human beings will have spread, colonized all over the galaxy on 10 billion places where we in principle could live if we organize the planets a little bit. And there we are everywhere. And the paradox is there are planets in our galaxy that are 10 billion years older than the Earth. Actually, most of the planets that resemble the Earth are much older than the Earth. So imagine a civilization that was 1 billion years ahead of ours, and was of our kind and spread around. They would have been here a long time ago. It would be them that had colonized the continents and not us. And there are no such space aliens. And this, I think, is very paradoxical, very strange that they don't come all the time. In Fermi's conclusion, which I again think is right, was that there are nobody like us anywhere in the galaxy. There are no other places where there is a technological civilization like ours that have reached this level that we are on today. It's very hard to believe, and once some say, shouldn't we be a little more modest than that or something? But maybe not. Maybe we are the super civilization of the galaxy, right? It's us. Yeah, wow, right? It's us. Yeah, we are special, right? Yeah, ooh, yeah. So maybe not. But then why are they not here? Why are the other super civilizations not come here? I will skip this thing in just to tell you, and this was what they ended up with. So let me just skip over very quickly here in order to end somewhat at the time I promised to end to why is it? I will just touch upon this thing with the water. How could it be that there are water here? Is that the thing that is special? It could be many, many things that are special. This could be one of them. There are many other things also. And you actually know it. If you take a glance at the moon, you see that it has craters, and it has big round craters like these up here that are called Mare area. One thought it was oceans in ancient time. These are big craters. This crater here is 1,000 kilometers in diameter. It's a celestial body of a diameter of 100 or 200 kilometers that have hit the surface of the moon with a speed of 25 kilometers per second. It's enormously fast. So it comes from somewhere out in the solar system and hit the moon. The big surprise, I think the biggest scientific discovery from the whole Apollo project, that was that they figured out, they were trained to find stones that were very old, older than stones on the Earth, in order to see what was the Earth and the moon like at time before continents had destroyed every material on the Earth. And they didn't find anything that was older than the Earth. In fact, they found that all the stones they picked up and brought home, they had the same age. They were 3.8 billion years old. This is the same age as a small region up in Greenland, which is the oldest part of the Earth's crust. Exactly the same age. And they're all this. It means that all the craters, it was all things that have splashed out of the craters they found. All the craters were formed at the same period, 3.8 billion years ago. There was a big cosmic bombardment 3.8 billion years ago. It has nothing to do with the formation of the solar system. It came much later. So it has also rained over the Earth, whatever it was, fallen on the Earth. And one can calculate it. One can just see how many craters are there. You can sum them up, count them, and see so how much material fell on the moon. And then you can recalculate so how much fell on the Earth. And if you do this simple calculation, there's nothing that can go wrong in it. You'll figure out that on every single square meter of the Earth's surface, there fell in this period 3.8 billion years ago 2,000 tons of material on every square meter of the Earth's surface. So it was a very, very heavy bombardment. That's why one calls it the late heavy bombardment. Something came from cosmos at this specific moment. If you think about from your basic chemistry in school, how much is the weight of 1 cubic meter of ice? It's 1 tons. I mean, so if you have 2,000 tons, it's the same as 2,000 meters of ice blocks stapled on top of one another if it was ice that fell. Right? It's 2 kilometers of ice that could have fell. It could be comets, right? They consist of ice. So it could be comets. If it was, there were 2 kilometers of water that came. This is exactly what we have in the oceans today. So was that where it came from? And if so, theories today tell us that if it was comet that bombarded, it was because of a movement of Jupiter and Saturn over a very particular configuration that happened 3.8 billion years ago. So was that it? Was that it? Was that what was so particular? Our solar system is particular by having Jupiter and Saturn, and they moved in a particular way that moved the water that was formed out there in the outer part of the solar system into the inner part of the solar system, where life can originate if it comes there. So let me just skip some of these things here of meteorites that fell. Here you see a fantastic one that fell over Lolland. So it's called the Maribor meteorite, and it's a very famous meteorite now because it's the first meteorite that we know for sure it was a piece of a comet that fell. It's because because of this thing here that it's a long story. I will skip that story. Only tell you that it was because of a man that was making wood up in Skåne, and he was annoyed that people came and stole his lumber during night time when he couldn't see it. So he put out such video cameras to see who was coming. And what happened right after he had put up the video camera was that came this comet that came in front of his video camera and fell over Lolland. And people found 15 grams of this, even though there had been tons of it. But they found a small piece of it and could prove that it was a piece of a particular comet that we know that it's called Encke's comet. And it fell on Lolland, and it's called the Maribor meteorite today. Such comets, if they had not been vacuumed by Jupiter in the very beginning, so that maybe the oceans where the life should originate on Earth came 3.8 billion years ago. If this has not happened, they would have come regularly nowadays, all the time. And sometimes if a big comet comes, it will strip off the atmosphere of the Earth. So we don't want them to come too often. We will actually want to exercise a little bit on how to move them away. And this is a great project. That it's another thing that I think we should focus on doing soon, figuring out how to move away these. And I think you will agree with me when I show you the last slide here. I have 2 slides after this. First, I will show you this thing here, which is a calculation by an insurance company. Because what is insurance companies? What is the kind of calculations that they're good at that they want to do? That is, they want to calculate if there is certain risk of a certain damage, how much shall it cost in order to draw an insurance against this risk so that we can also earn on it. Right? So the question here on this graph is how often does it happen that one is hit in the head by a meteorite? And what shall it cost if I want to make an insurance against being hit by a meteorite? Right? So there are all kinds of meteorites. The small ones, they're pretty harmless, right? And you can be lucky to sell them afterward if you're hit by one. So it's maybe even beneficial. And then there's a very big one. They come very rarely, so they are not so dangerous either. Even they make enormous damage if they come. So it's sort of the middle one that are the most dangerous one. They're the most expensive to draw an insurance against. So this graph here shows if a meteorite has this size here, how many people would on average die because of the impact. And you see 2 very interesting things here. Here is the only historical larger impact we know. It was a comet that was 50 meters in diameter, so it was just a little bigger than this room here. A nice block, but it comes with high speed. So it came in, pressed the air in front of it. It exploded in the height of 8 kilometers above a river that is called Tunguska in Siberia. Fortunately, very few people lived up there. The nearest people were 150 kilometers away from the explosion place. There went fire into the clothes of the people because of the heat from the explosion, 150 kilometers away. People that were 600 kilometers away in the coastal area, they were blown into the ocean because of the pressure wave from the explosion, 600 kilometers away. 2,000 square kilometers of forest just broke like this. Away from the explosion place. There's no crater, it exploded up in the air. So if you put all these things together, you can calculate how large was the explosion. It was about 1,000 times more energetic than the nuclear bomb over Hiroshima during the Second World War. 1,000 times bigger. It was just a nice clump of this size here. Now imagine that there come in ice clumps that are a little bit larger than this. So if it had been on an average place, about 10,000 people would have died from this impact in Tunguska. But nobody died because it was so remote. They come approximately once every 100 years. The last one it was in 1908, and now we have 2000, and now we're a little past that. So it could come any time. Be careful when you go home. Actually, if it had been 5 minutes later, it had been over Stockholm instead of over Siberia. But it was not. So it was over Siberia. So if they're a little larger, how many people will on average die? And you see when you come up to something that is just about kilometer size, the death rate is about 6 billion. So that's the end of civilization. If we're hit by a cosmic impact of 1 kilometer in size. Jupiter cleared away all these 3.8 billion years ago. So there are very few of them, and they come with very large intervals. They would have come all the time if it had not been this clearing up. So they come with very rare intervals, maybe 10,000 years interval. This is a time since the first agriculture. And during this time we have developed to understand that this is a problem. And we have almost developed a technique that we're able to move them away so they don't heat. But we'll have to work a little more on this. But we are almost there. And if we don't work on it, we will not survive long. So here I show you, and I don't know, can we dim the light a little bit? This is the last slide I will show, the one after this one here. This is the, these are all the bodies that are 1 kilometer or larger. Those that we would die if they hit the Earth. The civilization, it would be the end of civilization on the Earth if they hit. It is not a green color out here, it's green dots, right, that are out here. Here is Mars orbit, Earth orbit, Venus and Mercury. All those that are green, they stay out here, at least for the moment and for the coming many thousand years. All those that are red or yellow, they cross every year the Earth's orbit. There are pretty many of them. And what I will show you here in the next slide, that is an animation of 1 year from the 1st of January 2008 to the 1st of January 2009. How did they move during this year relative to the Earth? So you have the Earth, you will see the Earth here move around in its orbits, and you will see the other planets, and you will see these starting moving, and you'll see how they moved over. They are those. Here's the Earth. And here we have some, unfortunately, almost ones. Oops. So you maybe don't think about it when you have party and so. We go around just like in a Russian roulette around the sun, and here they come, boom, boom. Every one of them, if they hit, but they just pass, right? If they hit, it's the end of civilization. Any single one of these. So it's a great project to try to figure out, as a first exercise, where are they? Because we only know, it's only a fraction of those that are there. It's those that we know and that we have the orbit of. So this is a great coming project. So was this what happened? Is that why they don't come in their UFOs all the time? Because this was, it was more abundant in most places where they didn't have a Jupiter and Saturn. So they were much more dense than this. So they were hit all the time. So there was no time for civilization to develop. Is that the reason why they are not here? Or was it because water didn't come? Or was it something else? And as I understand, this is what some of you will tell me when I have a cocktail up there. What was the problem? So just thank you very much that you came in.
Yeah, thank you for such a fascinating talk. We have time for 2 questions.
Isn't it possible that Fermi is wrong, all respect for Fermi, with the Fermi Paradox? Because when I read about this for the first time, I always thought, what about the speed of light? I mean, what if all these planets are populated, but they can't get out of their solar system? Isn't it possible that you're just stuck there? Even if we think about technology and the future, isn't that a possibility?
Yeah, it's a possible solution to it, right? But I mean, one would also say, so why don't we at least hear the signals from them all the time, right? Maybe they are all waiting that the other ones are sending a signal because they don't want to be the first. They don't want to risk to be eaten by the other ones. So they wait to hear what the other ones are. And if everybody's waiting, there'll be nobody, right? So, yeah, it could, but it could also be, as you say, that it's not possible. There's some physical limit that we don't know about. It's not possible to travel between stars, but I think not. I mean, I don't know how to do it, but I think that I will not go into details. But these organizers, they are also physicists, and they know all the things that the more we know that there are much more we don't know, right? So. There's so many possibilities that in principle we are not able to do. In principle, you cannot maybe not travel faster than light. Maybe one can do one day, but maybe we can never do that. But at least in theory, it's possible to fault the space so that you don't have to travel very far to get to the other end of the galaxy. And so they will not be very far. You will think it's science fiction, but if you told the Vikings that we will sit here with our mobile phones, they will also think it's science fiction, right? So it's possible. It's physically possible. It's physically possible that there are more dimensions we can walk in and out of. It's physically possible that one can fold space and come there in a very small distance. So we come around this, we can go everywhere. We have no clue how we should do it, right? And we also don't know if in practice it's possible. But in theory, at least, it could be. So I don't think that this is the problem, but it could be.
Any last question?
Hey, I was just thinking that I wrote, 2 years ago or something that the Earth actually was created of 2 planets billion of years ago that collided, and just exploded. And after some time, the material created this moon and this Earth. Couldn't that be why there was the 2,000 of meters of material you didn't know where it come from?
Yeah, this thing that you mentioned there, that was how the moon was created, and that's also something that seems to be very special for the Earth. But that happened 4.4 billion years ago. One can date it quite accurately. So it's a little bit more than 4.4 billion years ago. But the event that made the craters on the moon, and that's a big discovery from the Apollo, it was 3.8 billion years ago. So it's 600 million years later. It's a long time. So it's not the same event. So there was an event 4.4 billion years ago, just when the solar system was forming, where people believe that a Mars-sized planet hit the Earth, and that made material go into space that formed the moon, and that's why we have such a relatively big moon compared to what other planets have. And this is something that in itself maybe is necessary for life, and it's a very peculiar event, because if the moon was not here, the Earth's axis would stand and wobble around, and it would be very unstable to be here. There would not be this stability that maybe biology requires over biological timescales. So maybe we would not have developed. So maybe that's something that was needed. But the thing that was the big impact of the 2,000 tons per square meter, that came 600 million years later. It's another event.
Okay, unfortunately there's no more time for questions now, but you can always catch Uffe at the bar. So now we're going to have a 10 to 15 minute break, and after that Rune Søchting and Jonas Olesen are going to present Soundworks, so stick around. But first, a last thanks for Uffe Gråe Jørgensen for this fascinating.